So we just studied the three measures of central tendency, mean, median, and mode, which are measures of the middle of the data. This is a measure of how spread out the data is. So sorry, let's go back to that. So it's a measure of how spread out the data is, which is deviation from the mean. So mean and standard deviation are very much connected. They're related to other. Standard deviation is a measure of how much deviation there is from the mean on average, so to speak. It's kind of a typical deviation from the mean. So this is the formula for variance, which you get standard deviation from because you take the square root of variance. So to get from here to here, you just take the square root. So the square root of whatever the variance is, and you get the standard deviation. So this first time, just so you have maybe a little bit of an understanding of what standard deviation is, we're going to derive it from scratch using the formula. So let's do that here and see if that works. Yeah, that works. Okay, so I'm going to go to Home and a new document, just start fresh and say no, don't save changes. And let's start with the list and spreadsheet page. So go up to the very top. So cursor up to the top, use your arrow keys to go up to the very top next to the letter A, and we're going to put XC for the name of the list. Never call a list one variable, call at least two. Sometimes it's a word like test, like scores or tests or ages or whatever. Okay, let's type in the data, 6.9, 8.7, 7.6, 4.8. And 9, make sure you press enter or mouse out of that last cell after you type that last cell. Now I've typed in all 5 terms. There are 5 terms. If I scroll up, I think I can see them all at once even. So that's all my data. What we're going to do is we're going to do this formula in reverse. So if you see this X, oops, let me get that back there. So if you see the X there, that is like your XC column there. Those are all your different X values, and there's 5 of them. X bar is the mean of the data value. So that means the mean. So X bar is the mean. So we could, let's do that. So let's add a calculator page. So I'm going to go to the calculator page, not a scratch pad. Don't go to the scratch pad, it won't talk. Don't hit that button. Definitely add it some page 1.2 now. I'll just do one variable stats. I think we did this the other day. Menu 611, one list. Right, use the right arrow there to choose one of those, and I'm going to choose XC. That's my only variable. And say enter, and the X bar right there at the top is 7.4. So the mean is 7.4 of this data. Okay, so X bar is 7.4 is equal to the mean, or X bar. Okay, let's go back to our list. So I'm going to hit Control left arrow to turn pages and go back to the list and spreadsheet. This is going to be the difference. So I'm going to take X minus X bar. So I'm going to call this diff, DFF, or difference. And in the formula bar, either going to click in there. I like to hit equal so I can do in Excel. And now I'm going to put in the formula. So we want to do X minus X bar. Our X is called XC. So XC minus X bar, which was 7.4. That was the mean. So we're going to take all those data values in the first list, and this will automatically subtract 7.4 from each one of them. So you see when you do 6.9 minus 7.4, you get a negative number. 8.7 minus 7.4, you get a positive number. So you have these positive and negative numbers. And that's part of the reasons why we do this next step of squaring these. So we're going to take all those values. So our next kind of work backwards in the formula is to square. So I'm going to call this SQUARE, or square. And in this cell, I'm going to hit the equals kind in the formula. And I'm going to take diff and square it. So diff squared. So all those values are squared. So negative 0.5 times negative 0.5 is negative 0.25. Right, just squared all those values. Those are all positive. That's important. I want them all positive. We're taking the deviations from the mean and we're squaring them. This symbol right here, that is the uppercase sigma, I believe, in Greek, and that means the sum of all those terms. So this is going to be the sum of those terms. So I'm going to let's go back to the calculator page. So I'm going to click Control right arrow, or go to the click up there. So I'm going to do sum. So I like to just type the word sum, parentheses, and then what do I want the sum of? I'd rather not type it from scratch. Let's see, sum of, I think our list was called, oops, definitely wasn't called that. I think it was called square, right? So SQ, there you are. So sum of all the squares. So that's the sum of the squares there. When I press enter, it says the sum is 11.3. It actually is right there. If you notice in your one variable stats, SSX is the sum of the squares. So we just did it by hand to get it. We're actually calculating something that the calculator will do here for us. So this is the only time we'll do it by hand, but we will do it this time by hand. So we get this 11.3. That is the sum of squares. I divide that by the number of terms. There were 5 terms, so divided by 5. I want a decimal, so I'm putting a decimal in there. So I get 2.26. So that is our variance. If I take the square root of that, I should get the standard deviation of 1.5. If you scroll up here, you can see that the standard deviation, the sigma x, is 1.5033. We get the same value there. By the way, if we wanted to, get the standard sample standard deviation, we could have taken that 11.3 divided by n minus 1. So n minus 1 would be 4. There are 4 terms there. And then square root that. And that would give us our SX, or sample 1.68. Yeah, 1.68 is our sample standard deviation. So SX is sample standard deviation. And sigma x, whenever you use a Greek letter, you're talking about the population. So the population standard deviation. Usually we take a sample from the population. And so you can see the calculator actually did all that work for us. It calculated both the sample standard deviation and the population standard deviation. So there's really no need to do those steps every time. What we're doing when we take the square root to get it back to standard deviation is we're undoing this square here. We squared them to make sure they're positive. We summed them up, and then we took the square root. It's kind of a strange formula, but when it works really nicely in stats, we use standard deviation, and it really is super helpful, actually. So I want you to type and find the standard deviation of this. So I don't want you to do it by scratch. I just want you to find it. So let me see if I can make this a little bit smaller. There we go. So you can see it all. Okay, these are hurricane strikes. I don't think I spelled that quite right. Hurricane strikes since 1851. Okay, so let's type this data in, and really all I need is the strikes column. That just tells us what decade that it was in, starting at that decade. So I'm going to go to the home key and insert a list and spreadsheet page. Go to the very top and put strikes. That was the name of this data. Start at cell A1 and type away, 19, 15, 20, 22, 21, 18, 21, 13, 19, 24. Do I have 10 pieces of data? I do. I always like to check that I put the right number of data pieces in. Hit the home key, go to a calculator page. Let's do one variable stats, and use 611. Right click, choose strikes. And it does all the work for us. It says that the mean, if you wanted to know it, is 19.2. I don't really need to know that. I think we were trying to find the samples. There's 2 different standard deviations. So sample standard deviation is 3.25, and population standard deviation is 3.09. So just slightly different numbers. It's saying typically, so the mean is 19.2. Just to understand what standard deviation is, typically you're going to be about 3 units, a little more than 3 units away from the mean, typically. So the mean is 19.2. So if you just pick kind of random numbers in there, you're usually about 3 units away from the mean is the typical deviation from the mean. That's what we're saying there. And we use this in stats a couple different ways. So first thing I need you to know, and you need to memorize these three numbers. I'll tell you what three numbers in just a second. These numbers are not important here. But this is the empirical rule. I'm not sure that this empirical rule is actually on the ACT yet, if I've seen an instance of that, but it's a good basic stat thing to know and to help you understand why we use, what's the purpose of standard deviation. So this is a big reason why we use standard deviation. So we memorize these three numbers. So the three numbers are, like this means the mean right there, so that's the mean in the center. And we're adding a standard deviation. That's what this is measured in. So the units are actually standard deviation. And when going in this direction, we're subtracting standard deviation. So that's one standard deviation below the mean. That's one standard deviation above the mean. This is two standard deviations above the mean. This is two standard deviations below. And same thing here for 3 below and 3 above. So our ruler or yardstick becomes how many standard deviations something is away. Okay, so 68% of the data is within one standard deviation from the mean. So 68% of the data, which means these are symmetric. So 34% of the data is on this side and 34% of the data is over here. If we go another standard deviation, so if we go 2 standard deviations each direction, this is the next number you need to memorize, is 95% of the data for a normal model. This is called, this is a normal curve. So sometimes we refer to this as the bell curve, but it has this kind of look, looks like kind of like the Liberty Bell or something, right? Has a bell curve look to it. And so we measure the bell curve in terms of standard deviations, and we can tell how unusual a piece of data is by how many standard deviations it is away. General rule of thumb, if something's more than 2 standard deviations away above the mean or below the mean, it's pretty unusual. It's getting to be unusual. Unusually high test score, unusually low test score, or whatever it is we're talking about for this information. So if you think about it, 95 minus 68, what is 95 minus 68? So it's going to be 7 and 8 minus, it's 27. So this section and this section add up to 27%, which if I divide that by 2, I get 13.5 over here. So 13.5 are in this section, percent. And in this section also 13.5 are in this section. That's percent as well. And so we use that nicely. And then there's also another one here. So if you go 3 standard deviations out, 99.7%, those are the 3 numbers for the empirical rule I want you to know, are within 3 standard deviations. So that's almost everything, really, when you think about it. So like all of this is 95. So let's do 99.7 minus 95 is 4.7. So between this guy and this guy, that's 4.7% total. So let's divide that by 2. And I think we get 2.35. So this part right here is 2.35%. This part right here is 2.35%. There's actually one little piece. It's possible with a normal model to get even some data that's past more than 3 standard deviations, extremely rare and unusual. So if you add those up, that's 99.7. So there's only 0.3 left between those little 2 n things. So this is 0.15 or half of 0.3, and this is 0.15. So anything below 3 standard deviations or above 3 standard deviations is only 0.15 in each direction there. So that should add up to 100%. Again, we use that to kind of take some data and chart it out. Let's see what this looks like. Okay, so the heights of the same variety of pine tree are normally, or we should probably say something like approximately normal. So approximately normally distributed. Nothing is perfectly normally distributed. The mean height is 33. So that you can see in the figure there that 33 is the mean height. We're going to add a standard deviation to the right, which is equal to 3. So this would be 36. We're going to subtract a standard deviation, which is 3 to the left. So this would be 30. And keep going. This would be 39. This would be 42. This is 27. And this is 24. So we've labeled everything we have to label there. And then they might, and again, that's we know between 30 and 36 for tree heights, 68% of the trees are between those values. Between 27 and 39, 95%, the vast majority of trees are between those values. And so this is a lot of data, surprisingly, ends up being approximately normal. So a lot of data kind of scrunched in near the mean, and then not as much as you get further away. So this one says for a population of male European eels, the mean body length is 15.7. So 15.7 is in the middle here. If I got one standard deviation above, so if I add a standard deviation, this is how I do this. And you don't have to do it this way, but it's kind of a neat way of doing things. Okay, so 15.7. I'm going to type that in my calculator and press enter. I'm going to say plus 2.8. And it always takes the previous answer. If I press enter 3 times, it gives me the next 3 numbers. So 18.5, 21.3, and 24.1. 21.3 and 24.1. Okay, let's do that again. So if I take the middle, 15.7, and then subtract, so I want answer minus, 2.8. Hit enter 3 times, and it'll do it for you at 12.9. Just trying to save you some more, 10.1, and 7.3. So now it asks a little more detailed question here. It says, approximately what percent of eels are bigger than 12.9? So 12.9 is here. So we want all that area that way. Well, we know, if you remember, this is 34%, right? You know all those percentages, but if you look at the big picture, like isn't this exactly half the data if you go to the right, 15.7? Splits it in half. So that's 50% of the data plus 34 is exactly 84. So this first question is 84% of the data is between those two things. What percent of eels are between 10.1 and 18.5? So I see they're picking these standard deviations. So this one's 34%. This one's 34%. I believe from memory this is 13.5%. Here's adding those up. 68, 78, 81.5. So I think that would be 81.5% if you add up those 3 values. So this is kind of interesting. So men in America are normally their heights are normally distributed with a mean of 69.5. So that's like the average or typical adult male, with a standard deviation of 2.5. So 69.5 plus 2.5 is 72, 74.5 and 77. Subtract 2.5 is 67, 64.5 and 62, I believe. Okay, I've got all that. Draw and label a normal curve. And so the question is, about how many would you expect to be taller than 6 feet? Well, 6 feet is, we've got to think that through. 6 feet is what? 72 inches, right? So 72. So anything bigger than 72. So between these two, I think we're 13.5. If you don't remember that, that's okay. Because really, remember, this is 34% is here. So I actually do know, if you go this way, that's going to be 84% of the data, right? Because you've got 50% or half of it is this way, plus the 34 is 84%, which means by default, this must be 16%. So what's interesting about that is, so 6 feet, I think this data is actually real. So only 16% of the population of adult males are more than 6 feet tall. So like my sons, like Matt's 6'4", Josh is 6'2", Caleb right now I think is 6'1", he's still growing, I think. And I'm 6 foot and 1/2 inch. So all 4 of us are in that 16%. But there's a bunch that are not. And so if this is 72 is 6 feet, this would have to be 6'5", which means there's only 0.15% of the population of adult males that are taller than 6'5". So that's extremely rare. Like some NBA players are taller than 6'5", and that's not very common, right? I mean, 0.15% of the population of adult males taller than that. So it's kind of interesting. So in this end, 72 and 62, this would be 5'2", so 5'2". Again, only 0.15% of males are below, more than 3 standard deviations below the mean, or smaller than 5'2" there. So it's just an interesting way to look at things and kind of categorizes how unusual it is. Again, typically more than 2 standard deviations away from the mean is how we might classify something as unusually large or unusually small kind of a thing. So it's actually a very helpful measure when using the normal curve. So we use standard deviation quite extensively with the normal curve. I'd say it's one of its main purposes. We use it in some other ways as well, but that's what you need to know.